In this video, we are going to discuss the definite integral. So I'd like to remind us that what we are trying to do is we want to know the area under the curve f of x from x equals a to x equals b. And let's draw down a picture of that again on how we were going to estimate that. So this is a reminder from a few videos ago. But if we have some function here, f of x, some positive function here, f of x, that's really how we determine that we're finding the area under the curve, from the curve to the x-axis, from x equals a to x equals b here. And what we can do is we can make a bunch of rectangles that we will calculate the area of. And then we will add up the areas of these rectangles. And when we do that, we will get an estimation for the area under the curve f of x from x equals a to b. And what we have here is we can have 1, 2, 3, all the way up to some number n, number of rectangles here. And when we do something like this, we say that the summation of the areas of these rectangles is called a Riemann sum. And we can write out a Riemann sum on n intervals, or n rectangles, as, and now we'll use that sigma notation that we introduced in the last few videos. Oops, so this is the sum from k equals 1 to n of f of x sub k star, I'll say what that means in just a moment, times delta x sub k is equal to s sub n, s for a sum using n rectangles or n intervals here. Now what is all of this? Well, this is the sum on n rectangles where delta x sub k is the width of the kth rectangle, and then x sub k star is some x value in the kth interval. Reminder, when we were doing the sums of these rectangles, when we were calculating or estimating the area under the curve in previous videos, we did stuff like R8, which meant use the right hand limit and you find the area of 8 rectangles. Well, the right hand limit is just a specification on which x within each interval to use. Truthfully, though, we don't actually care whether we use the rightmost point, the leftmost point, the midpoint, or just some random point in between. So we just say x sub k star here to be some point. We use some point in each interval. It doesn't actually matter which one we use. And so what does this mean? That means that f of x sub k star, if we just evaluate the function at that point, that is the height of the kth rectangle. Okay. And so what do we have here? We have the width of each rectangle, the height of each rectangle. We multiply those to get the area of each rectangle, and then we add up as the number of rectangles goes to n here, right? We get the first rectangle, the second rectangle, the third rectangle, all the way up to the nth rectangle. And so that is our Riemann sum on n rectangles. All right. So what can we do with all of that? Well, using that, we may recall that as the number of rectangles goes towards infinity, the area under the curve approaches the true area, or our estimate for the area under the curve approaches the true area under the curve. And so that's how we define our definite integral. So the area under the curve, f of x, when f of x is a positive function, from x equals a to x equals b, is, and that is the limit as n goes to infinity of these Riemann sums. So the k equals 1 to n of f of x sub k star times delta x sub k, and this is our definite integral, which we'll write out the notation for now. That is the integral symbol from a to b of the function f of x dx. Now what does all of this mean? Right here we have the integral sign, which we had introduced previously when we talked about indefinite integrals. The a, the thing that goes at the bottom here, is our lower limit of integration. In other words, it's the x value that we start integrating at. B is the x value we end at, so the upper limit of integration. F of x is just the function we are integrating. Whoops. The function we are integrating. And dx is the variable we integrate with respect to. In some sense, we almost think about this as the height of the function times the width of the function, but the width of the function is going off to 0, so we have some differential here that represents the infinitesimally small width of the interval. And so we multiply those together, and then we add up or sum up, right? That's what this integral symbol means. We sum up from a to b. And that's essentially what's happening. It's sort of what this notation means, but you should just think of it as the definite integral from a to b of f of x dx, where f of x is the function we're integrating, dx just is notation to tell us what variable we are integrating with respect to, and the bounds or limits on our integration are from a to b here. And this is, of course, true when this limit exists. All right. Let's write down just a couple more things in this video then here. If this limit exists, f is said to be integrable on the interval a to b. And I have one quick theorem we want to write down before we conclude this video. If a function f is continuous over the closed interval a to b, or if f has finitely many jump discontinuities, just a quick reminder, a jump discontinuity means that your function goes from one point to another finite value, so from a finite value to a finite value, and that is our discontinuity there. We go from a finite value to another finite value. So as long as we have a finite number of these happening on the closed interval a to b, then the definite integral for the integral from, which is our notation for that, is this integral sign from a to b of f of x dx, exists, and so f is integrable over the closed interval a to b. All right, and that is how we want to end this video.